Chapter 11, Nukes. In this chapter, we will explore the nuclear chemistry. There are some early discoveries in nuclear chemistry. In the 1890s, Wilhelm Röntgen was the first to discover X-rays and use them to take pictures of his wife's hands. A French scientist named Antoine Becquerel, while studying how light affects specific rocks, found that certain rocks emit an unknown kind of powerful energy. The energy was being emitted with no input of anything, all on their own, without being heated or subjected to an electric current. Becquerel's rocks glowed in the dark. A young woman scientist from Poland, Marie Curie, was the first to characterize and measure these mysterious emissions and termed them radioactivity. By the mid-1930s, scientists had begun to learn about the atom and its contents. At this point, the two charged particles, protons and electrons in the atom were known. The existence of neutrons had been documented. It was known that atoms of an element could have different numbers of neutrons, which were named isotopes. Chemists and physicists had begun to use beams of neutrons to perform experiments on radioactive materials that release energy or particles when their nuclei undergo reactions. An Italian physicist named Enrico Fermi decided to bombard every element one at a time with a beam of neutrons to see how each one responded. In Fermi's experiment, the most interesting result he obtained was with uranium, the element that has 92 protons in its nucleus. When bombarded with neutrons, uranium produced a mixture of unidentifiable products. German chemist Ida Noddack suggested that the uranium atom was breaking apart and making two lighter atoms of similar mass. Later, Lisa Meitner confirmed that uranium does indeed split to produce krypton and barium. Nuclear fission, the splitting of the atom's nucleus, had been discovered. To recognize Meitner's critical role in the discovery of nuclear fission, element 109 meitnerium was named in her honor in 1997. Nuclear reactions differ from chemical reactions. Chemical reactions typically involve the rearrangement of electrons and chemical bonds being made and broken. In contrast, nuclear reactions change the number of protons and neutrons in the reacting atoms. There are two major classes of nuclear reaction: fission and fusion. A quick review of what we learned in Chapter 2. The superscript is the mass number, which is the sum of the number of protons and neutrons in the nucleus. The atomic number is shown as a subscript before the element symbol. The atomic number is the number of protons in the nucleus of the atom, which could be found in the periodic table. For a given element, the atomic number is always the same because the number of protons defines the element. If we want to find the number of neutrons for a given isotope, we subtract its atomic number from its mass number as shown below. Mass number minus atomic number equal to number of neutrons. Because atoms of an element can exist as different isotopes, the mass number identifies the specific isotopes of the element. We often say atoms of an element name followed by a number to refer to the specific isotope of that element. For example, uranium-235 indicates the mass number of that uranium atom is 235. You can find the atomic number of uranium is 92, then you can calculate the number of neutrons is 143. A fission reaction involves splitting a nucleus and forming two new nuclei. As in Fermi's experiment, he smashed uranium-235 with a neutron. The atom divides into krypton-91 and barium-142. 3 neutrons are also produced. The neutron in this nuclear equation is depicted as a letter N with a superscript 1. Its mass number is 1 because it is just a neutron, so the sum of its protons and neutrons is 0 plus 1 equal to 1. Its subscript is 0 because it contains no protons. The picture schematically shows the nuclear reaction. We can also write it out in a way similar to how we write a chemical equation. In a chemical equation, every atom shown on the left must also appear on the right. Atoms change places as electrons rearrange. Phase of each compound may be indicated. In a nuclear equation, mass numbers and atomic numbers are usually shown with the element. Atoms appearing on the left side do not have to appear on the right side. Instead, the sum of the mass number on the left usually equals to the sum of the mass numbers on the right. The same is true for the subscripts. No phase indication is needed. One thing in common for both chemical and nuclear reactions is that coefficients could be used to balance the equation. Let's count the protons and neutrons in the equation for Fermi's uranium experiment and see if it is balanced. For each symbol in this equation, the number of neutrons and protons is listed in the figure below. To verify if a nuclear equation is balanced, we sum all of the superscripts on the left and sum all of the superscripts on the right. If the sum of the superscripts on both sides is equal, the equation is balanced. The same verification should be performed for the subscripts as well. Note that in the nuclear equation, there is number 3 in front of the neutron as a multiplier. It tells us that there are 3 neutrons on the right side of the equation. Nuclear and chemical reactions differ in another way. Nuclear reactions produce more than just few elements. They also produce an energetic product that can be either a particle or a radiation. Radioactive decay is the process by which certain isotopes give off those energetic products. Isotopes that undergo radioactive decay are radioactive isotopes. There are 3 important types of radioactive decay: alpha, beta, and gamma. Alpha decay occurs when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons. Since 2 protons and 2 neutrons combined are identical to a helium-4 nucleus, sometimes the symbol for alpha radiation is written as helium-4. The equation to the right shows Hassium-273 breaks apart to give Seborgium-269 and an alpha particle. Hassium here is an alpha emitter. Beta decay occurs when an unstable nucleus emits an electron. How does a nucleus which contains only protons and neutrons emit an electron? In some unstable nuclei, a neutron changes into a proton and emits an electron. The -1 reflects the charge of the electron, which is equivalent to an atomic number of -1 in a nuclear equation. When an atom emits a beta particle, its atomic number increases by 1 because it then has an additional proton. The example below shows the radioactive Neptunium-239, a beta emitter, emits a beta particle to become plutonium-239. Notice that the nuclear equation is balanced. The sum of the mass numbers on both sides is equal, and the sum of the atomic numbers on both sides is equal. The third and final kind of radioactive decay is the emission of gamma radiation. Alpha and beta radiation exist in the form of particles, but gamma radiation is a form of electromagnetic radiation. Recall from Chapter 2, gamma rays are high-energy, short-wavelength photons that have no charge and no mass. When a gamma ray photon is emitted from a radioactive atom, it does not change the mass number or the atomic number of the element. Gamma rays are usually emitted from the nuclei in conjunction with other types of radiation. The equation shows Hassium-273 breaks apart to give Seborgium-269, an alpha particle, and gamma radiation. Nuclear chemists often do not include gamma symbol because it doesn't affect the balance of the nuclear equation. Therefore, this nuclear equation can be written with or without the gamma. It is understood that gamma radiation is often present even if it is not included in the equation. Each type of radiation affects the body in a different way. We will explore these in the later slides. In general, the amount of energy released in nuclear reactions is much greater than the amount released in chemical reactions. The combustion of 1 mole of natural gas, methane, produces 550 kilojoules of energy. Nuclear reactions, on the other hand, are typically about 1 million times more energetic than combustion reactions like this one. Nuclear reactions can create a huge amount of energy, and nuclear power plants based on those reactions are an obvious source of energy for human society. But they also produce radioactive waste, which poses an enormous environmental challenge. Nuclear power is attractive because it presents a way to generate energy without relying on oil and coal, both resources that are present in limited quantities and increase greenhouse gas emissions. However, that uranium is not an unlimited resource. A finite amount of uranium is left in the Earth for us to use. The figure on this slide is an illustration of a typical nuclear reactor. The reactor core is located in a containment building. The hot radioactive material is kept there. A fission reaction produces enormous amounts of heat energy in the core, and this energy converts the water passing over the fuel into steam. The pressure of the steam drives a turbine connected to an electric generator, which converts the energy of the rotating turbine to electrical energy. The steam leaves the plant at the top of the cooling tower. Within the core, control rods can be lowered into the radioactive material to damp the nuclear reaction and prevent overheating of the reactor core. We refer to the field in nuclear reactions as fissionable material. One field used commonly in fission reactors is uranium-235. A collision between one neutron and one atom of uranium-235 initiates this reaction, which produces 3 neutrons. When these 3 neutrons are released, they smash into 3 more uranium-235 atoms, each one reacting to produce 3 more neutrons. Because this reaction amplifies itself by initiating more reactions, we refer to this series of fission as a chain reaction, as illustrated in the figure on the right. In looking at the figure, we can see how much a chain reaction could rapidly go out of control. The number of fission reactions quickly escalates, and because heat energy is produced in each step, the reactor can easily overheat if the reaction is not kept in check. If the acceleration is sufficiently fast, the result is an explosion. For this reason, the amount of uranium used in nuclear reactors is crucial and carefully regulated. To prevent explosions, the minimal amount of fissionable material necessary to sustain the chain reaction, called the critical mass, is used. If the goal of the fission reaction is not to create power for our energy needs, but instead to create an explosion, as in an atomic bomb, then a critical mass of radioactive fuel is also required. However, with a bomb, the goal is destruction. To that end, it is desirable to have an uncontrolled chain reaction. Thus, unlike in nuclear power plants, no safeguards are in place to prevent the reaction in an atomic bomb from happening. The key challenge that arises in creating a bomb with critical mass is premature detonation. To circumvent this problem, some fission bombs hold 2 separate portions of fissionable material, each portion having a mass less than the critical mass, which is called a subcritical mass. When a bomb is discharged, the chemical explosive is detonated, forcing the 2 subcritical masses to smash violently into each other. The total mass of fissionable material becomes critical, and an explosive chain reaction is initiated. The figure to the left is a schematic of an atomic bomb. The first fission bomb was dropped by the United States on Hiroshima, Japan on August 6, 1945. Radon is a noble gas that has an atomic number of 86. Radon gas does not interact chemically either with itself or with other substances, but radon is highly radioactive and it decays to produce an alpha particle and gamma radiation as shown below. When we think of exposure to radiation, we normally worry about accidents at nuclear power plants or exposure from nuclear weaponry or X-ray machines. However, radiation is also a natural phenomenon, and radioactive materials are found in Earth's crust. There is radioactive uranium in the ground in many regions across the United States. Areas with numerous deposits of uranium also have higher levels of radon found in homes. The figure below is a map of radon levels across the United States. Red areas have the highest levels of radon, orange areas have moderate levels, and yellow areas have the lowest levels. Radon is one of the elements that form as uranium-238 decays in a series of sequential nuclear reactions. Sequential strings of radioactive reactions are common because a radioactive asymptote often forms another radioactive asymptote, and the process continues until a stable asymptote is reached. These sequential reactions are known collectively as radioactive decay series. The figure below shows the radioactive decay series that produces radon-222, beginning with uranium-238, which exists in deposits in the Earth. A sequence of decay events leads eventually to radon-222, a gas. The radon-222 continues to decay until it becomes lead-206, which is not radioactive. Along the way, alpha and beta particles are emitted. How to determine how long a radioactive element will give off radiation? Scientists use the term half-life to define the time it takes for 1/2 of a radioactive sample to decay. The half-life of radon is 3.8 days. If there is 1 gram of radon today, in 3.8 days there will be 0.5 grams of radon. In contrast, the half-life of uranium-238 is 4.5 billion years. The longer the half-life for a given radioactive element, the more slowly the element decays. The figure below illustrates how the amount of a parent radioactive material decreases over several half-lives as it decays to make its daughter material. After 1 half-life, 1/2 of the material has decayed. After 2 half-lives, just 1/4 is left, and so on. Eventually, such a small amount is left that it can no longer be measured. Of all the isotopes in the uranium radioactive series, why do we worry most about radon-222? The answer is that only radon is a gas, and it sifts from uranium deposits in the ground and enters buildings through cracks and fissures in their foundations. Also, all the reactions from radon-222 to lead-206 happen very fast. The radioactivity formed during these reactions, which includes 4 alpha particles and 4 beta particles, is released quickly as radon decays. If a person inhales radon, and the radon decays before being exhaled, the decay products can damage lung tissue. In the US, more than half of the radiation an average person exposed to in a typical year can come from radon. The number is greater than the exposure from all other types of radiation combined. Although people living in areas of known uranium deposits are probably more likely to have high levels of radon in their houses, the values from house to house can vary. This depends on the construction material used, the age of the building, its ventilation, and several other variables. The only way to be sure about the radon level in your own house is to have it tested. Different types of radiation penetrate matter to varying degrees. Alpha radiation is the 18-wheeler truck of radioactivity. The alpha particle is by far the most massive of all particles emitted by radioactive nuclei. Consequently, alpha radiation has the most potential to interact with and damage other molecules, including biological ones. Highly energetic radiation interacts with other molecules and atoms by ionizing them. When radiation ionizes molecules within the cells of living organisms, the cells can usually repair the damage. However, in some cases, the cells can die or begin to reproduce abnormally. Alpha particles, because of their large size, have the lowest penetrating power. In order for radiation to damage important molecules within living cells, it must penetrate into the cell. Alpha radiation does not easily penetrate into the cells because it can be stopped by a sheet of paper, by clothing, or even by air. Consequently, a low-level alpha emitter that remains outside the body is relatively safe. However, consuming large amounts of the alpha emitter can be dangerous because the alpha particles then have direct access to the molecules that compose organs and tissues. Beta radiation is the four-door sedan of radioactivity. Beta particles are composed of electrons only and are much less massive than alpha particles. Because of their smaller size, beta particles have a higher penetrating power, and only something as substantive as a sheet of metal or a thick piece of wood stops them. Consequently, a beta emitter outside the body poses a higher risk than an alpha emitter. If ingested, however, the beta emitter does less damage than an alpha emitter. Gamma rays are the motorbikes of radioactivity. It is the most dangerous because it can penetrate most kinds of matter, including human tissue. Imagine a motorbike zipping through a traffic jam. Shielding gamma rays requires several inches of lead or thick slabs of concrete. Because gamma radiation has strong penetrating power, it is used in medicine for the treatment of tumors. The irony of nuclear medicine is that, along with destroying cancerous tissues, the process kills healthy cells as well, making many patients undergoing radiation therapy very ill. Radon undergoes a nuclear reaction that produces alpha radiation. Inside the body, alpha radiation is much more harmful than beta radiation because the alpha particle interacts with tissues in very localized areas, can irreparably damage the tissue in those small areas. Some medical procedures require the patient to ingest a radioactive tracer to visualize the abnormalities in the human body. For instance, technetium-99 is useful for monitoring the brain and the heart as well as regions of arthritis or bone cancer. Radioactive iodine is used to image the thyroid gland. The SI unit for the amount of radiation a human being is exposed to is the sievert. In nuclear medicine, the commonly used unit for effective radiation dose is the rem, which stands for Roentgen equivalent for man. By definition, 1 sievert is equal to 100 rem. A typical person is exposed to about 0.3 rem every year, and symptoms of radiation sickness begin at doses of 25 rem. Radiation affects the fast-growing tissues in the body, because each new cell is exposed as it is created. Thus, the lymph nodes and the bone marrow are among the regions of the body hit hardest by high doses of radiation. Leukemia is the most common type of cancer associated with radiation exposure. Question 1. Which was the first scientist to use the term radioactivity? A. Wilhelm Röntgen, B. Marie Curie, C. Antoine Becquerel, D. Enrico Fermi. Please pause your video here. The correct answer is B. Marie Curie. Question 2. Suppose an atom of uranium undergoes fission, and one of the atoms that forms is cesium. What is the other element that forms? A. Rubidium, B. Barium, C. Strontium, D. Xenon. Please pause your video here. The correct answer is A. Rubidium. In a nuclear equation, the numbers of protons and neutrons are usually balanced on each side. Therefore, from the question, You begin with uranium, 92. You get it from the periodic table. It breaks apart to form a cesium. Cesium from periodic table is 55. And give you something with a atomic number. So therefore, you're going to use 92 minus 55. That gave you 37 for the number of protons or atomic number. So go to the periodic table, find atomic number equal to 37, which is Rb, rubidium. Question 3. How many protons are in an asymptote of selenium 75? A. 75, B. 79, C. 34, D. 41. Please pause your video here. The correct answer is C. 34. All isotopes of the same element have the same number of protons. Isotopes are different only in their number of neutrons. Selenium is element 34 on the periodic table. It has 34 protons according to the atomic number. Question 4. How many neutrons are in an isotope of gold 195? A. 195, B. 197, C. 116, D. 76. Please pause your video here. The correct answer is C. 116. Gold has an element symbol of AU from the periodic table with atomic number of 79. 79 goes here, and then on the top is the mass number, which is the 195. The question is asking you how many neutrons in here. So you use the mass number minus the proton, that gave you the neutron, which is 116. Question 5. What is the name of an isotope of copper that contains 35 neutrons? A. Copper 6, B. Copper 29, C. Copper 35, D. Copper 64. Please pause your video here. The correct answer is D. Copper 64. From the periodic table, we know copper has an atomic number of 29 with 35 neutrons. So you do 29 plus 35. That gives you 64 for the mass number. So we can simply call this as copper 64. Question 6. What is the name of an isotope of oxygen with 9 neutrons? A. Oxygen 9, B. Oxygen 8, C. Oxygen 16, D. Oxygen 17. Please pause your video here. The correct answer is oxygen 17. Oxygen has atomic number 8. The atomic number is the same as the number of protons. So proton plus neutron, given the question, equal to the mass number. So mass number goes on here. Therefore, we can call this as oxygen 17. Question 7. How does someone determine if a nuclear equation is balanced? A. The sum of the atomic numbers and the sum of the mass numbers on both sides of the nuclear equation are equal. B. The sum of the atomic numbers on both sides of the nuclear equation are equal. C. The sum of the mass numbers on both sides of the nuclear equation are equal. D. The sum of the atoms on both sides of the nuclear equation are equal. Please pause your video here. The correct answer is A. The sum of the atomic numbers and the sum of the mass numbers on both sides of the nuclear equation are equal. In a nuclear reaction, atoms do change from one element to another because the number of protons in the nuclei change. Therefore, we can verify that a nuclear reaction is balanced by checking that the subscripts on the left equal to the sum of the subscripts on the right. The same thing is done for the superscripts. The superscripts and the subscripts are referred to as the mass number and the atomic number respectively. In contrast, in a chemical equation, every atom shown on the left must also appear on the right. Question 8. Which type of radiation is a particle that can be represented by a helium asymptote? A. Beta, B. Alpha, C. Paston, D. Gamma. Please pause your video here. The correct answer is B. Alpha. This is the symbol for helium. As you can see, the mass number is equal to 4 and atomic number equal to 2. According to the definition of alpha decay occurs when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons. So the 2 protons, you can tell by the atomic number here. And in order to get the 2 neutrons, 4 minus 2, that gave you the 2 neutrons. So the correct answer is B, alpha. Question 9. What type of radiation is emitted when Neptunium-239 decays into Plutonium-239? A. Alpha, B. Beta, C. Gamma, D. Electron capture. Please pause your video here. The correct answer is B, beta. Between Neptunium and Plutonium, the mass number stays the same. They are both 239. Therefore, the particle emitted has negligible mass, or to say the mass is nearly equal to 0. Beta decay occurs when an unstable nucleus emits an electron. The electron has a mass that is negligible compared to protons and neutrons. Question 10. Fill in the blank. Choice A, Lead-210, B, Polonium-211, C, Polonium-210, D, Lead-211. Please pause your video here. The correct answer is Polonium-210. Our goal is to find out the symbol and also write out the superscripts and the subscripts. Bear in mind, in a nuclear equation, the sum of the mass numbers, the superscripts, on the left equals to the sum of the mass numbers on the right. The same is true for the subscripts. So therefore, the superscripts is 210 on the left. It equals to 0 plus something. To solve the something equal to 210 because 210 plus 0 equal to 210. This is the superscript. And then on the subscript side, it's equal to 83 minus 1 plus what number gave you 83. To solve this, you get 84. So the 84 goes into the subscripts. And then you go into the periodic table, find atomic number equal to 84. That's polonium. So therefore, the correct answer is C, polonium-210. Question 11. Where does the fission reaction take place in a nuclear power plant? A. Reactor core, B. Transformer, C. Cooling tower, D. Steam line. Please pause your video here. The correct answer is A. Reactor core. In a nuclear power plant, the fission reaction takes place in the reactor core inside the containment building, which is right here. Transformer is here. That's not. Cooling tower, this is the cooling tower. That's no. And steam line, which is right here, which is also a no. Question 12. What is the name of the process that can be rapidly go out of control if too much uranium-235 is used in the fission reaction? A. Decay reaction, B. Chain reaction, C. Control reaction, D. Combustion reaction. Please pause your video here. The correct answer is B. Chain reaction. A collision between one neutron and one atom of uranium-235 initiates this reaction, which produces 3 neutrons. When these 3 neutrons are released, they smash into 3 more uranium-235 atoms, each one reacting to produce 3 more neutrons. Because this reaction amplifies itself by initiating more reactions, we refer to this series of fission as a chain reaction. Question 13. Fill in the blank. The spent fuel rods are blank. A. No longer radioactive, but they must be safely stored on site. B. Still radioactive and should be safely stored on site. C. Still radioactive and can be incinerated. D. Shipped to Yucca Mountain. Please pause your video here. The correct answer is B. Still radioactive and should be safely stored on site. Please refer to the nature box in this chapter. Question 14. 3 neutrons are produced from the fission of 1 uranium-235, and each neutron initiates subsequent fission reactions. Assuming this process continues step by step, determine how many neutrons are produced after the third step in the chain reaction. A. 3, B. 9, C. 27, D. 81. Please pause your video here. The correct answer is C. 27. From the question given, we know that each neutron will give 3 additional neutrons. Therefore, the base is 3. You do it 3 times so that you use 3 multiplied by 3 multiplied by 3, you get 27. Other than solving this problem mathematically, we can do it in a more visual way. So you begin with 1 neutron. By step number 1, that's your step 1, you have 3 neutrons. Each will split into 3 more neutrons. This is by step number 2. And then each of these 9 neutrons going to do 3 more. I'm really running out of space, but if you continue counting all of them, you will realize that there are 27 by step number 3. Question 15. In a radioactive asymptote, what percentage of the parent material remains after 4 half-lives? A. 3.25, B. 6.25, C. 12.5, D. 25. Please pause your video here. The correct answer is B. 6.25. Half-life is defined as the time takes for 1/2 of a radioactive sample to decay. So therefore, imagine that you begin with 100%. By the end of the first half-life, you're down to 50%. By the second half-life, you're down to 25. By the third, you're down to 12.5. By the fourth, half of 12.5 is 6.25. So therefore, by 4 half-lives, you have 6.25%.